Now, in the third part, we consider n by n system. See, here is n by n system, so the number of equations equals the number of unknowns, the number of variables. So we first see the matrix form of this system. Before we just look at the original linear equations, and now we focus on matrix form, because if you use matrix form later, you'll find you can do much simpler calculation. So we like matrix form. So n by n linear system, here we have m equations and n unknowns. And in fact, this linear system can be written in matrix notation here. Okay, so we have this matrix. This matrix is an n by n matrix. The first row is A11, A12 till A1n. The second row is A21, A22 till A2n. The last row, the mth row is AM1, AM2 till AMn. We have this matrix. And we can also write all the unknowns x1, x2 till xn in this form as a column vector here. So it's x1, x2 till xn. And the right-hand side vector, you just write b1, b2 till bm here. So all the given data in the linear system are now written in matrix form. Right? And in fact, we give this name for this matrix. It is a coefficient matrix. So any n by n linear system, you can write as a matrix form. Remember this? And we can see a simple example. Now, this is a 3 by 3 linear system. Okay, and immediately we drop out those matrix, coefficient matrix. Okay, so the first row is 1 to 1, comes from the coefficients of the first equation of those unknowns. Okay? The second row is 3 minus 1 minus 3. And the third row is 2, 3, 1. So we have this coefficient matrix. And we also write the unknowns x1, x2, x3 in this form. Okay? And the right-hand side data, we just write here, 3 minus 1, 4. So we call its right-hand side vector later. You will know this. So this 3 by 3 system can be written just as a matrix form here. It's very easy to obtain, right? So it's a 3 by 3 matrix form of this linear system. Okay. Now, we give a definition for augmented matrix. When an n by r matrix B is attached to an n by n matrix A, the augmented matrix, we can denote it by this way. Okay, parenthesis, on the left side is matrix A, and the right side is a B. We use a vertical line to divide it into two parts. Okay, so here, given you A here is an n by n matrix. Yeah? The matrix B here is an n by r matrix. Okay, we have the same number of rows, but a different number of columns. And then you can write A, B together as an augmented matrix. Okay, the left side is just A, see? And the right side is B. Here is an example for linear system. You can just write it as an augmented matrix, see? Even simpler, right? This augmented matrix, the left side are the coefficients of the unknowns of the linear system. And the right-hand side vector here, you just write as the B part, right? It's 3 minus 1, 4 here. So giving you this augmented matrix, immediately you know what the original linear system is. And given you this linear system, you can immediately write the augmented matrix here. Okay, so now we transform a general n by n linear system to this augmented matrix. Okay, and now we consider how to solve this linear system, how to use this augmented matrix to solve this linear system. Okay, so here we use also 3 row operations. So 3 row operations can be applied to the augmented matrix. So the first row operation is interchange 2 rows. Now we just consider the matrix. We don't consider the equations. So we just interchange 2 rows of this matrix. Okay. And the second row operation is we multiply a row by a non-zero real number. And the third row operation is you can replace a row by its sum with a multiple of another row. Okay, we have these 3 row operations. And see this example. We have this augmented matrix. So the left part is the coefficient matrix, and the right-hand side vector are written here. Okay, now we want to transform this augmented matrix to simpler form. Okay, so the first row, we take it as a pivotal row. And we use the 1, 1 entry here to be the pivot element. We use this pivot element to eliminate all the other numbers in the same column to be 0. Okay, so we do this row operations. So in order to transform, to eliminate this number 3 to be 0, we use a multiplier -3. So we use -3 times the first row, then we add to the second row. So we will get here is 0, here is -7, here is -6. And at the same time, here also you use -3 times 3, you get -9, and here is +3. So -3, -1, you will get -10 here. And similarly, we also want this 2 in the first column to be 0. So we use a multiplier -2 times the first row. We will get here is 0, here is -4 plus 3, here is -1, and here is -2 plus 1, here is -1. Here is -6 plus 4, so it's -2. Okay, so using these operations, in fact, we use operation 3 to get the second augmented matrix here. And after we get here, see, using this -7 here, 2 entry, -7 here, we can eliminate the 3 2 entry here to be 0. So the multiplier should be -1/7. So we use this multiplier and then times the second row, add to the third row. So eventually you can get this augmented matrix. Okay, this augmented matrix is in triangular form, right? So the coefficient here is just in triangular form. So immediately you can get a solution, right? From the third row, you will get -1/7 times x3 equals -4/7. So what is x3? So x3 should be 4. See? After you get x3 equals 4 here, you substitute here, and use the second row, you will get x2. And similarly, you substitute x2 and x3 here in the first row, you will get x1. Now, for this n by n system, ask you to solve this system. Try to solve it in non-matrix form. We don't consider the equations form, okay? We consider its matrix form. Okay, so given this a 4 by 4 linear system, so we just write its augmented matrix first. So the augmented matrix is the first row 0, -1, -1, 1, 0. Okay? Just from the first equation, you can get all the entries here. And from the second equation, you will get the second row here. So it's 1, 1, 1, 1, 6. Okay? From the third row, third equation, you will get third row. Okay, it's 2, 4, 1, -2, minus 1 here. And from the fourth equation, you'll get 3, 1, minus 2, 2, 3. So this is an augmented matrix. Okay, for this matrix, how can we transform it to a triangular form, to simpler form, using the 3 types of row operations? How can we do this? Here, the 1, 1 entry is 0. This may cause some difficulty, right? Before we use this 1, 1 entry to eliminate all the other entries in this column to be 0. Here it's 0, so we can't use this. Then how to do next? I think we should using row operation 1, right? We interchange the 2 rows. Okay, so we interchange the first row and the second row. And we get the new augmented matrix here. After here, we can do as before, right? You're using this 1, 1 entry as a pivot element. And using the first row as a pivotal row. So the first row, pivotal row, you keep the same. And for the pivot element, you try to use this to eliminate this 1 to be 0, this entry to be 0. Okay, so minus 2 times the first row, add to the third row, right? And also minus 3 times the first row, add to the last row. And you will get this new augmented matrix. So they are equivalent, okay? So after you get this augmented matrix, now how can we do this? You just use this entry to be the pivot element, right? This row to be the pivotal row, and you will get this form. So this form is in triangular form. We get it, right? This is triangular form, so we get x4 equals 2, right? Because here the fourth row means minus x4 equals minus 2. So x4 equals 2. And after you substituting x4 equals 2 here, you will get x3. And using this row, you'll get x2. Using this row, you'll get x1. Okay, so you can solve the linear system just using matrix, augmented matrix. You just use the row operations on augmented matrix, and you can solve this linear system. So for n by n system, we can solve those systems using augmented matrix. So the row reduction can be done recursively like here. So there are numbers at the beginning here, and the first step, you're using this number to eliminate all these numbers to be 0, yeah? You'll get this one. And the next step, using this entry to be the pivot element, this row to be the pivotal row. You can transform this part to be like this. So after this, you will get the triangular form. So one question is here. However, the procedure may be break down if all possible pivot elements are equal to 0. For example, like this. If the matrix like this, because all the possible pivot elements are 0, so you cannot get a triangular form. Even you cannot get triangular form, you can try to make it simpler. And this is what we will learn next. Okay, so before ending this lecture, we have some remarks. If an n by n linear system can be reduced to an equivalent triangular form after n-1 steps, then it will have a unique solution that can be obtained by back substitution. Remember, back substitution. Okay, first get the last variable, you get the value for 8, and then the next one, till the first one. Okay, so the reduction procedure will break down if at any step all possible choices for pivot elements are equal to 0. When this happens, how can we do next? So the alternative is to reduce the system to certain special echelon form, or we say it's a staircase shaped forms. And if the augmented matrix, you transform it as echelon form, then 2 cases for the solution set may happen. First one, no solution, or infinitely many solutions. For the second case,